Okay, so maybe we can start. So it is my great pleasure and honor to welcome you to this CTU HKIAS Institute for Advanced Study, distinguished lecture by Professor Alain-Sol Sznitman from ETH Zurich in Switzerland. So first, I would like to thank our guest speaker, Professor Sznitman, for accepting our invitation to CTU, and the Hong Kong IAS for making the talk and the visit possible through their generous financial and administrative support. Thank you. So Alain-Sol Sznitman has been a full professor in the Department of Mathematics at ETH in Zurich, so the Swiss Polytechnic Institute, since 1991. He has been a director of the FIM, the Mathematics Research Institute, there from 1995 until 1999. So let me first give you a short biography of Professor Sznitman. So Professor Sznitman was born in Paris in 1955. After studying at École Normale Supérieure in Paris, he became an attaché de recherche at CNRS, the French research agency, and worked at the probability laboratory, Laboratoire de Probabilité, at Université Pierre et Marie Curie, which is also known as Paris 6 or now Sorbonne Université. So he worked there for 4 years, from 1979 to 1983. And then he moved to the Courant Institute at New York University for 2 years, and then came back to Paris for 2 years, from 1985 to 1987, as a chargé de recherche CNRS. Then in 1987, he moved back to New York following his appointment as an associate professor at the Courant Institute, where he became a full professor in 1990. Let me say that Professor Sznitman received many prestigious awards, including an Alfred P. Sloan Fellowship in 1989, the highly prestigious Rollo Davidson Prize for Young Researchers in Probability in 1991, and the Liner and Michel Loewe International Prize in Probability in 1999. So this last prize is actually widely considered to be the most prestigious prize in probability theory, awarded every 2 years at UC Berkeley. So Professor Sznitman was also a plenary lecturer at the first European Congress of Mathematics in Paris in 1992, and an invited speaker at the International Congress of Mathematicians in Berlin in 1998. In 1997, Professor Sznitman became a fellow of the Institute of Mathematical Statistics. In 2008, a member of the Academia Europaea. In 2012, a member of the inaugural class of the American Mathematical Society Fellows, AMS Fellows. And in 2014, a member of the IMU Circle, so the International Mathematical Union Circle. Professor Sznitman is a leading specialist in probability theory, especially on questions about random media originating from statistical physics. And he made major and deep contributions, in particular to the study of Brownian motion among random obstacles and the analysis of random walks in random environments. In the last 15 years, he studied the disconnection of a piece of material by a random walk. And this problem is at the same time very easy to formulate, but extremely challenging to study mathematically. And for this question, he introduced a completely new mathematical object called random interlacement that he then studied extensively. This is the main topic of today's talk, entitled Disconnection, Random Interlacements, and the Gaussian free field. Okay, so please join me in welcoming Professor Sznitman for this distinguished lecture.
Well, thank you very much for this introduction, and also it's an honor for me to be giving this lecture. I expect that several words in the title are mysterious to you, and hopefully by the end of the lecture it will be less so, and they will be less mysterious. The story I'm going to tell will try to reflect some of the developments that happened over a course of about 10 years, a bit over 10 years. And it will also show that a number of the findings that happen come out of serendipity. So chance is there, a major player in how things turn out. And you can say for someone studying probability, this is quite normal. But it's an interesting fact of life. So let me start that story. So I'll start the story with this termite in a wooden beam. So here is the story. Around 2005, Amir Dembo, his professor at Stanford, came to ETH and told me of a very intriguing problem, a question asked by a physicist from Orsay, a university south of Paris, Hilhorst. And here is the kind of problem he was asking about. So you have a beam and a mathematician beam. So it's a piece of material which is infinite in one direction, and the base, which is represented there, is large. And this is a mathematician's toy, so it's periodic. But you can forget about it. It's irrelevant for what I try to convey. And it's discrete, so only these kind of intersections here are there, but the solid lines are not there in between. So this is this kind of discrete cylinder, so this is this beam. And in this beam, you have a malevolent being which is moving, and this is this termite. And the termite starts, say, on the floor 0 of that beam. It's doubly infinite, so there is floors going all the way down, all the way up. And it's moving in a very random way. So each time it decides, well, I'll move there to the one of the neighbor. It doesn't know. It picks at random. It moves. So it has a very kind of erratic motion, and it goes on. And it's creating some kind of destruction. And the position here, these are these symbols, but this is irrelevant. The question that Hilhorst was asking is, at what point is it the case that the destruction is so serious that if you pull on both ends of the beam, it gives up, and it's just broken, moves away. And this is this disconnection time in kind of technical terms, but this is irrelevant for the lecture today. So, so the question of Hilhorst was, how long does it take for this kind of local destruction to have an effect which is really felt on a global way, in the sense that the material is broken? And of course, you can ask other questions, which are, where is the random walk at the time where it's creating that last and definitive step, which is breaking the piece, and what does the material look like from there? So, so Amir Dembo and I started to think about this. It was kind of hard to just visualize what it was. And I'm not expecting that you can visualize right away. So here is one way for you to visualize better. So here, the piece that you see here, it's at the time where the material breaks down, and you are looking at what remains solid, not broken, which is going to the bottom floors. And here is how it looks like. So this is a simulation from Laurent Gergen. And so this is the tip where it's broken, and we are moving down on that material. And as you move away from this breaking point, it becomes more and more solid. And you have some effects of periodicity, but you see it become more solid. And at the time, so a bit later, so we worked on that, and Amir Dembo and I had the first rough result, and it was saying that in a very rough way, the time it took to do this major damage in this beam was of order the square of number of sites in the base. So this is the mathematical translation of that. It's a very rough result because it's just ratios of logarithm for those of you who are mathematicians. So it's a very rough way to get that order. But this is what we got at the time. OK. So then came a bit later, so around 2006, so a question came from Itai Benyamini, and who is a mathematician in Rehovot in Israel. And he was asking, well, this work about this termite and eating up in the beam. So, well, there is this other problem which looks also pertinent to some of the methods you developed there. So here is the kind of problem. It's now you have a large periodic box of side length n, and you have, think of a termite, if you want, which is walking in that structure. And again, it's something which is destructive, so it's a malevolent being. So later on, I will give another interpretation, which is not in this destruction mode. But then the question of Itai Benyamini was, well, if the walk or this termite moves for a time which is proportional to the total number of sites in that box. So if you look at what's still standing after this destruction there, is there a big chunk there or only small chunks? Okay. So this is a kind of question which is in the realm of what happens in random graph theory, where there is the paradigm of the giant component. So there are kind of situations where you have an existing very big components, or you are in a mode where all the components are very small. And the question of Itai Benyamini was, is it the case that there is anything like that, or not? So again, here is something where you can have a feeling of what's going on. So here, so you have this periodic box. It's maybe hard to see, but here it's the proportionality factor. So here it's 0.5 of the number of sites. And here it's a slice in the middle of that box. And you are seeing in black the pieces where the termite has gone. And here in blue, so in red, you have the structure which is still living. And in blue, you have so it's the biggest component there. And in blue, it's the second largest component. So let me move the effect a bit. So you see the middle slice is getting darker and darker. But there is still a very big structure which is there. And now I'm here at that point where, so I'm at 2.50. So the number of steps of this termite has been 2.5 times the total number of sites. So this is the largest component which is still standing after all this damage, and that's the second largest. And you see in the slice here, it's almost all destroyed, so on a horizontal plane. And let me just give you the animation of how things. So there is more and more destruction going on. So there is a receding of the biggest, and at some point, the second and the largest one are going to the same size, and after they vanish. and then after it goes on and it disappears. So at the time, so the methods were unsophisticated, and with Itai Benyamini, so it's in 08, so we were able to show that for a small u, typically, and when the box is large, there is one big component which is remaining. And we had not much control on what it meant, a big component, but we had a notion of a big component. So this was the status of things in year 0708, so 2007 or 8. And what was missing somehow was to have some kind of local model. You see, so here the missing piece was you had these global objects, which was the beam or this large box. But there was no model to say what was happening close to a point. And this is a kind of a paradigm from mathematicians. It's the fact that the so-called infinite lattice, which is the ZD here, the d-dimensional lattice, well, it's infinite, but actually it's modeling not something infinite at all. It's modeling the microscopic worlds in an object. So you are zooming in close to some point, and you blow up the image, and you obtain something like this, and something like this. And this in blue, it's the termite at work. What is the trace which has been left? So, and what was somehow missing at the time, it was precisely to have some kind of model which describes the structure which is there. And this is precisely these random interlacements which are this model. So I'm going to start with one way to describe these interlacements, and it's a dry way. It's a very quick way, but it's extremely obscure. It gives you a formula. It's telling you that for every u, that's the u from this simulation of the cube before, there is a unique random set in the infinite lattice, which has the property that if you want to evaluate the probability that it misses a finite portion of the lattice, this is this k, so this is exponential minus u times the capacity of k. And there I'm somehow banking on your memories from high school, where this capacity here, it's a kind of discrete version of this electrostatic capacity that you have most likely seen in high school, and it corresponds to the total charge of a conductor, which is brought to a potential 1, and at infinity there is a potential 0. And there is a total charge, which is this capacity of k. So, so this formula is extremely compact. It's a quick formula. It totally determines the object. On the other hand, it's very cryptic. So it's hard to read much on it, except that you see that as you let u becomes bigger and bigger, so this thing is decaying to 0, and it's telling you that it's harder and harder to miss that set k. And indeed, as u goes on, this random set becomes bigger and bigger. So the bigger u, the bigger IU. So this IU, this is the random interlacement at level u, and its complement, it's the vacant set at level u. And I'm going to give a slightly more visual description of it by explaining how it functions in a box, just in a finite piece of the lattice, which for the convenience of the drawing I take as a box, but actually it doesn't. So you have a box, and you have, I talked about this electrostatic capacity, so you have a notion of equilibrium measure, which to each point of the box tells what's the charge that you put on it in order to have this potential which is equal to 1 on the box and decaying to 0 at infinity. And the capacity is just the sum of all these charges which are there on the boundary of the box. And what you do in the first step is that with a proportionality factor independently on each side, which is here on the boundary of the box, with a proportionality factor u times this charge at the point, you draw, you choose randomly the apparition of points. So there is a kind of technical device that probabilists use very much. To do that, it's called the Poisson measures. So it's a way to choose randomly such points, and you obtain something like this. There might be several sitting on the same site, but for the readability of the picture, I'm not doing that. And once you have chosen this point, well, you just let a random motion, as the termite before, evolve from each of the points. And that gives you a picture like this. And the thing is in high dimension, it's dimension bigger or equal to 3. So at some points, it leaves and never comes back again. It might do some coming back, but at some point, it will go forever out. And the thing is that this way of producing a picture is exactly telling you how this random interlacement looks in the box. So it's less economical than such a formula, but of course, in terms of intuition, it is incomparable. So this is something on which you draw a lot of independence and you understand a lot of the picture. This is something which has the virtue of Fermat's last theorem. You can put it on the side of a book, but it's not bringing you necessarily such an insight. Okay, so once you have this object, so it has this property that as you let this parameter u increase, well, it's something which is getting thicker and thicker, so it's increasing. And it's a model now which has the property that there is no special role of the origin, so it's translation invariant in this mathematical jargon. And it has something which is a very special property, which is the fact that it has a very long-range dependence in the fact that what happens at a point and what happens at another point, so it's somehow decaying like 1 over the distance to the power d minus 2. So in dimension 3, it would be d minus 2 is 1. Okay? And so this is this long-range dependence which is there. So this object was somehow introduced with the goal of having some insight about these problems of destroying a material. And so here are some properties which have to do with the, let's call it percolative properties. So the questions which have to do with are things connected or not connected, and what's the size of the components. So there is, with that model, something which is atypical. It's the fact that the interlacement set and this complement are very different objects. And this is not the kind of cup of tea from the usual percolation models, because the basic model from percolation, which is the Bernoulli percolation, where every site is occupied or vacant with independent probability, well, it's just a flip of the other set which is happening there, so there is no conceptual difference between the two. In that model, it's quite different. And what happens is that automatically this random interlacement, they constitute a connected, so it's just one piece subset of the infinite lattice. And you should think now of these blue lines as threads, not as a termite trajectory anymore. And in that sense, what you have is something which is a fabric. So it's something which is having this connection property like a piece of fabric, a material that you are wearing. On the other hand, for the, if you look at the complement of it, so the vacant set, well, if the level, so if the U is small, so if there are not too many trajectories, well, there is in this vacant set an infinite component. And if you go above a certain threshold, well, all components are finite. So you should think of it as a kind of transition of a fabric which is becoming a kind of a rainproof material in the sense that the complement of it is just having small pockets or it's having a big pocket. So if the level of threads is high enough, so the complement is just made of finite pockets. But if it's not, well, you have an infinite component. And to prove that, it took some effort because there is all these problems of long-range dependence, which is underlying there. So there are further critical values. I'll describe them briefly. The theory is, at present, trying to ascertain that these three things are just one. Actually, that there is just one object. So it's one of the challenges of the theory. But let me describe for you these levels, what they mean. And in some sense, there is a level which is this U star star, which is bigger than this U star. And it corresponds to a so-called strongly non-percolative regime of the vacant set. And what happens there is that, well, if you take a large box and the box of double size, which is there, you are not going to see any connection, so it does not happen. You don't see any connections between the boundary of the smaller box to the boundary of the larger box. And this one has a size which is double of that one. If you decrease the U, and a priori U star and U star star are the same, but for the way definitions are made, if you decrease to something which is below that U star star and hypothetically would be bigger than this U star, so what would happen is that you would be in a regime where you would see such connections like this, but you would not see something linking to a precise point. So if you choose a point, say the origin, there you won't see anything like this. But you could have, in that regime, which most likely does not exist, it's in the process of being worked out, so you would not, you could find connections like this, but you would not find something connecting to a specific point. And if you get to something which is less than this U bar, which is there, you are going to be in a regime where there are not so many trajectories of the thread, and it's strongly percolative for the vacant set. So I'm talking about the vacant set there. And what happens is that if you take two boxes like this, which are the same, and a bigger box, well, you find in it components which have a diameter comparable to the size of the box. So they will have a size comparable to those of the little box. And actually, they are going to be closely linked, still within the box which has a double size of these there. Okay? So there is a kind of local connection which is taking place in the vacant set, and this is this strongly percolative regime. Okay, so this is to give you a flavor of what are the role of these critical values which are there. But in most of what I will explain, I will take the stand to simplify the results that they are all and the same, just the same, in order to state things in a more straightforward way. So then there was a lot of work which, with important contributions from Czerny, Drewitz, Popot, Prokasia, Rat, Rosenthal, Sapochnikov, Teixeira, and I'm forgetting names there. There are a number of other names. And the results were showing here that, so this fabric is a very good network. So it's extremely well connected. So locally, so there are very good estimates telling you that even when U is small, so there is not that many threads, it's still very well connected. And the same is true if you have your U, which is in the strongly percolative regime for the vacant set. So you have the fact that the vacant set is also a good network, and that's measured in a number of things by looking at a typical distance from the origin, whether that compares to the Euclidean distance, or looking whether the heat equation on these structures is having a normal diffusive behavior. So there are a number of things. And concerning the equality of this, so now there are a number of results which are in the process of evolving for this equality of U star equal U star star. So it's due to progress in percolation theory on these sharp transitions. Okay, so let me go back a bit to what these results on this local model were bringing as information already on the initial problems that I mentioned. So this termite in the wooden beam and the fragmentation of a big box. And as I mentioned before, to make things simple, when I state the results, I'm going to pretend that we know that these critical values are one and the same. So the initial result with Amir Dembo was just saying that the logarithm of the disconnection time, it was behaving like n, like 2d minus 1 log of n. But actually, what one has now is that if you take the ratio of Tn to the square of the number of sites in the base, this is something which is behaving as a random variable, which is very close to something which is a kind of very studied object connected to something which is the model for random walks seen from far away and at times which are piled up. And this is the so-called Brownian motion. So if you take the long view and you step away from the beam, so the vertical position of this termite is something which is behaving roughly like a Brownian motion. When you take the suitable units in the height and in the time, the way you measure time. So I won't get so much more into that. And what happens is that here, the point where the disconnection will happen, this is the point where the local time, so this is a way to measure for the Brownian motion how much time it spends at a certain level, at a certain height, well, it reaches this critical U star. So now this is linking this kind of object from the microscopic world, this local model, to something which was the original model on this chunk of wood which is eaten up by the termite. And so when that level reaches this critical value, this is where things start to break down. Okay? So this is giving you a flavor of what could be here obtained for that problem. And for the fragmentation problem of this large periodic box which is eaten up for a time proportional U times the number of sites in the box. So what you obtain here, and these are with the works which are quoted up there. So what you obtain, so it's that for u which is less than the critical value, well, there is a actually unique giant component in the complement of the trajectory of this termite or outside the threads of this fabric. And if u crosses that value u star, well, all the components are small. So you have broken the structure into very tiny pieces. So they just remain small components. So this is, in a nutshell, what's going on there. Okay. So, so now let me come to another player, so which is coming in that field. So this Gaussian free field is an important model coming from statistical mechanics, but in probability has gained a lot of traction, and that's, it's kind of a funny story because it was maybe something valued a lot by physicists, and then somehow there were insights coming from probability that the physicists had not really measured, and there was a kind of back and forth, and the object now is a kind of a dual being valued by different communities and with different price. And to describe in a nutshell how this looks like, so you start by having a box in the infinite lattice, the d-dimensional lattice ZD. So you take a finite chunk, and you are trying to construct a random function which you force to be zero outside the box. So it's outside the box, it's forced to be zero, and otherwise it's going to have a freedom to have the value it wants at any site, except that you penalize it, and you penalize this freedom of choice with something which is an important quantity. It's this so-called Dirichlet energy. So it's looking at the value at a point, and at the neighbors, it's just doing this sum, and it's taking the square. So it's penalizing two big differences between neighbors. And this is exponential minus 1/2 of this thing, which is this energy. And that gives you, for a finite box, a well-defined way to define a probability density on functions that vanish outside. And then what you do a limiting procedure. You let the box grow and grow out to infinity. And what happens, and this is due to the fact that we're in dimension bigger or equal to 3, it's that this random object stabilizes. It has still a memory somewhere that it's forced to be zero out there, far out, but it's not oscillating wildly, and it tends to an object which is this Gaussian free field. So this is the Gaussian free field on ZD that I've described for you. And this object now, here it was definitely not something where every point in the lattice played the same role, because outside the box was not like inside the box. But after the limiting procedure, every point is just playing the same role. So you have forgotten what the origin is. So this is a beautiful thing. And it has a similar long-range dependence, which is the fact that if you measure what happens at a point X and at a point Y, and you try to look at the covariance, how that moves together, you find again this kind of decay, like the distance to the power d minus 2, and in dimension 3, d minus 2 is just 1. So this was, in a nutshell, the Gaussian free field on the discrete lattice for you. All right, so now comes chance again. So in 2011, it was the 70th birthday of Raghu Varadhan, who is a very prominent mathematician at Courant Institute. And there was this conference, and there Leibovitz talked to the guest of honor, so gave a talk there, and he mentioned several problems. as teasers for the birthday boy. And one of these problems is what I'm going to explain to you now. So this is something which was coming from the old ages, the other millennium. So it was it's 1983, so not 17. No, 1983 and 1987. So people had looked at the question of looking at this random function and setting some level and looking whether if you are above a level, well, can you move out to infinity from there on? Can you move without having to go below that or not? And so there had been a first paper there in it. So the question was implicit in the work of Molchanov and Stepanov there, but it was really heart of the matter in that paper, which was in theoretical physics style. And the reason that they, together with Jean Bricmont and Mace Leibovitz had obtained, was the fact that, well, if this level h was below 0, so definitely there was an infinite component. So this is this notion h star is bigger or equal to 0. It means that if you are looking at something which is negative as you want, well, you can move out to infinity without going below that negative level. And it was, in that paper, they could only show that this transition level was really something finite occurring in dimension 3. And there was a big obstruction in the proof they had devised at the time, and that was exactly the essence of the challenge to the birthday boy in 2011. That was in Taiwan, that conference. And I was there, and somehow it had the flavor of something I had seen in a slightly different context. And what happens is that together with Pierre-François Rodriguez, who was a doctoral student at the time, so well, we obtained the result that indeed this transition was finite for all d bigger or equal to 3. And we could achieve the fact that the transition was something strictly positive in large dimension. So this, maybe I'll come back later to that, but so this is something important because it's telling you that you can go above the, you see the 0 level is special because out at infinity, this random function is having the memory that it is pinned to be 0. But you can move above it and still have a kind of clear view and have a path going out to infinity. Now, the proof there was using the technology, which I did not describe for you, but of random interlacement, which was somehow dealing with these long-range dependence, and there was what people call renormalization. So you have a kind of induction along a sequence of scales, and but it's not the purpose of the lecture today, so I won't get into that. But actually, and that's where somehow things took a strange turn, it was much more than just, well, the methods apply well. Well, the methods were applying well because there was something other at somehow playing out in the background. So we come here to a topic which is, there is a deep link between these Gaussian free fields and the occupation times of random walks or Markov chains. So it's something which started out in the physics literature in work of Szymanczyk, and it was for mathematicians very, let's say, challenging because a lot of the expressions were infinite. But after there was versions by Bridge, Fröhlich, and Spencer in '82, which was in a discrete setup and which was making sense of these objects. And there was an important conference in Varena, I think, and where Dinkin was there. And Dinkin heard of these results, and somehow it stimulated very much his imagination, and he gave a version of these results which made a lot of sense for probabilists. I won't say what it is. And there was a lot of work, and in particular, more recently, work of Szabo and Tares, but it has been a very growing field. And now, for our purpose, here is the kind of situation that happens. So Titus Lupu had the interesting idea, which was to put back in fame something that people, especially in probability and not only probability, had been trying to move away from. So it's these cable systems. So cable systems, this is that. So instead of looking at the discrete lattice, well, you replace each, you insert between each neighboring site a solid rod. So it's something which looks like this. So, so you have these solid rods, and you can play with it if you want, if you feel like it. So this is these cable systems, and this had come in the work of Varopoulos much earlier in studying the bounds for the heat equation on discrete graphs. And it had been used as a technical device, and after there had been a method, a way to get away from it and directly work on the discrete structure due to Karn. And somehow here, Titus Lupu took the thing again in a different, with a different angle, and that happens very often in mathematics. And what turned out is that you can somehow construct objects on this bigger space, on bigger structures, so you have inserted a continuum between any discrete points, and you can construct at the same time in your Gaussian free fields tending to zero morally at infinity, and these random interlacements on these cable systems, which in such a way that your interlacements, they are sitting in the portion of space where the Gaussian free fields is below the level square root of 2u. And you have just some pockets here where it's bigger than square root of 2u. So you can construct the two objects on the same piece, and you have a kind of network of highways, which are these interlacements, which are sitting inside the landscape of this Gaussian free field on this continuous structure. And of course, things work well by restriction to the discrete structure, because after all, you have constructed bigger objects on a much, on a bigger space. And what you obtain is that on the discrete structure, your vacant set is at level u is containing the level where phi is bigger or equal to square root of 2u. And in particular, you have out of this way to couple things, to make them together, immediately the fact that the h star is less or equal than square root of 2u star. Actually, it's believed to be strictly strict inequality on ZD, but at the moment it's unproven. It's just on certain networks where one can do that. So, so what happened there was so what came out, so that's so it's a sequence of works where there was a previous work linking the interlacement to the Gaussian free field of mine, but it was on the discrete structure. Then Lupu had this wonderful idea, and then there was I introduced a kind of refinement of that, and what that gives you now is that you have a kind of very efficient highway in the sub-level sets of this Gaussian free field where it's less than square root of 2u. And this is a very powerful tool because, for instance, that came in a very, very major way in a very recent work of Drevitz, Prévost, and Rodriguez. So where they are able to show, using this network of highways, that, well, if you go at a slightly positive level, well, the set where the Gaussian free field on ZD is bigger or equal to h, this is strongly percolative for small positive h. So in jargon, it's just a mathematical jargon. It's proving that this h bar is strictly positive. It's an important accomplishment, and actually the proof does not only work for ZD, it works for quite a few other kind of networks. But this is not what I want to talk about so much today. So this tells you the fact that so here it was really this serendipity in full work, because the connection came out of this conference where Leibowitz was mentioning a problem from the 80s. And it looked like what was going on at the time on a different subject. And actually, there was a kind of merger of these two subjects. So they are, the proof worked because the two objects are very closely linked. OK. So I want to give also a little hint of a different kind of problem set where quite a bit of progress has been happening. So there are some questions that where you are stressing your system, and the response to this stress, which is an atypical constraint, is giving you a deep insight on the system. And here is one of these kind of stress that I want to talk about. And so what you are doing is that you take some kind of model shape. So this is this bean and you create a large discrete being by blowing it up and just restricting it to a discrete size. So this is the discrete blow up. So it's kind of, if you want, this is the bean, but now you have a mesh which is here, and you have just grown the bean out of proportion. So this is this n which is there. And the kind of question that you are going to ask is this disconnection event. It's you have a box of a large size of order n. You have this model here, and your interlacement, you want to know whether it's something which is typical, so for this random fabric, that it's blocking out this bean from the boundary of the box. So is it something which happens with grace, or do you have to force it? And if you force it, in what way? So this is what I mean by you are stressing the system, and the answer to the stress is giving you an insight on how the system functions. So the question is, how costly is it to have this disconnection here by this interlacement at level u? OK. So again, I'm stating the results pretending that we already know. It's not the case, but that these critical values are the same. If you are above this u star, which is u star star, you are in a regime where, well, your fabric IU is Hehn-proof. So it's isolating anything you want. So it's kind of, there is no cost It's something, disconnection is happening with a typical probability of close to 1 when n is large. So there was no stress there. On the other hand, if you are in the case where u is less than u star, well, actually, so you are in a regime where it's something which is not a rainproof fabric, so there are a lot of connections which are normally going out to the box. And it's costly. And there it came out of a series of work, so I'll give some comment in a minute. The probability of the disconnection is something which is behaving like exponential, a certain constant. So here there is this u which is less than the u star, so it's a strictly positive quantity. And here the quantities that you have is an n to the power d minus 2. So n to the d minus 2, this is something which is not the usual cost that you have in percolation. The usual cost that you have in percolation is that to create an interface, it's something which is proportional to the perimeter of the interface. So it's n to the d minus 1. Here, not so. It's less costly to do it. It's something like n to the d minus 2, and there is a proportionality factor, which is now the good old electrostatic capacity. So really, in the continuum, having your conductor A, so the beam A, and having potential 1 on it, and letting the potential decay to 0 at infinity, and looking at the total charge on that conductor there, on A, and so that's the kind of result that happened. Now, as I said, these questions are interesting because they force you to do two things. Typically, you have to prove a lower bound and an upper bound. It's not obtained by an equality. The lower bound is a reflection of the kind of scenarios that you can produce by imagination on how to disconnect. So that's somehow a reflection of your imagination. So this is a certain strategy. There is a technique which is called the change of probability method. It's using entropy inequalities, so which is giving you these lower bounds. Now, you can come with any scenario you want. That's very good for you. Now, the thing is, does it match up with an upper bound? So is it something, such a scenario, such a strategy to disconnect? Is there something saying that there is nothing really better? And this is what's involved in having an upper bound. So here, maybe I'll say after a bit of a word. So let me just say a bit of a word on how this functions with these lower bounds. The strategy that we use there with Shini Li and myself, so it was constructing an object which is giving a version, so it's the so-called tilted interlacements. So it's a kind of interlacement with a slowly varying parameter. And the parameter is such that it's increased so that it's something which is higher than the U star on the beam, and then it's decaying slowly to infinity. And actually the square roots, because it's the square roots of these parameter, so they decay like an equilibrium potential. So this is, in a nutshell, and I don't want to get into anything technical, this is the essence of the lower bounds. It's having something which is slowly moving to increase the parameter, put it in a mode where it's in a thick mode above the beam, and this is disconnecting. And you release it slowly at infinity. There is a trace everywhere of the fact that you have increased things, but it's done in a small way. There is a decay which is there. The upper bounds was challenging, and actually, so the first method, which is going back to 2014, was working a priori for an A, which was not a beam, but something which was like a box, and it was working for something convex. And getting from something convex to something non-convex was quite challenging. So there was a serious technical, more than technical, there was a serious difficulty there, to the point that some people said that, well, it's not at all, the lower bound is wrong. This is, you guess it, but it's wrong. But actually, no, it's that. And that somehow involved so certain notions of coarse graining. So there is a kind of, I'll show you a picture, and there are some solidification estimates. And the picture, it's just to give you a kind of flash of a picture. You see, you have to construct something which is in a vague sense a kind of a porous interface, which is creating zones where you are disconnecting. And it's not a real interface. It's something which is extremely unstructured. And this is related to, well, this kind of solidification estimate that something like this is as good as having a solid line, somehow solid interface. And you have actually no control on the regularity of these configurations. So this is the difficulty has to do with the fact that you don't have an assumption that it has finite perimeter. Or it's a different set of assumptions that you are dealing with. So that came out of this work with my doctoral student, Maximilian Nitschner. And there has been further results by Alberto Chiarini and Maximilian Nitschner showing that indeed, if you condition on such a, if you look at what happens when you disconnect, well, it's something which is in line with the strategy of the lower bound. So there is, and this is, on the technical level, it's one thing to know that you have the right orders of here of decay, but knowing that when you condition, it looks like what you are saying in this thing, it's still another level, because there could be, you had one good strategy, but maybe there are a couple of other good strategies which are producing the same kind of effects. And there it's kind of saying it really looks like that lower bound strategy which is there, if you know that it's disconnecting. And I think I've exceeded your patience by a few minutes even. So I think on these good words, I'll thank you.
So are there any questions from the audience?
What was the origin? You said that Amir Dembo
Yes.
Proposed this, what?
No, he did not propose. That was coming from this physicist in Orsay. So that was here from this very first thing that I was mentioning. The physicist was asking about this picture that I showed. So how long does it take to do it? And it was kind of an incentive to understand how this happens. And the simulation there.
You know what was the physical problem that was behind?
Oh, there you have different physical. You have even I discovered that people even were using models of that sort in biology, where you had some kind of destruction by enzymes of gels, and you had it was a way to release energy by breaking into small pieces or keeping one big piece. So in some sense, the problem came under different angles, and actually after it came with this angle of a Gaussian free field, it's, as I said, it was an excellent problem because it's still unresolved. What's the exact nature of the material at the point of the break? You have seen this simulation that I showed. It's a very dramatic kind of landscape. And the fact of going to the disconnection point puts you right away in this kind of critical mode. So there is a wording for that, but I won't say. But you are having a phenomenon which is putting itself right away in the critical mode by staring at that. And so in that sense, regardless of what it was modeling, it was an excellent question. At least for a mathematician.
I have a really general question. So
yeah.
It's really clear at the beginning you start with ZD.
ZD, yes. Yeah.
So this is really highly connected.
Yes.
So if I start with some structure is loosely connected like trees.
Yeah, so, or there was, yes. So there was some, yes, so here, yeah, so yes. So there, the theorem I quoted by Drevitz, Prévost, and Rodriguez, it answered an open question, which was, well, something which is dear to someone coming from Switzerland, corresponding to a graph which is the Toblerone bar. So it's, what's the graph I'm talking about? It's something which is the base is a Sierpinski gasket. And it's otherwise product with Z, so it's kind of the product of that. So Toblerone bar, let's say. So it's not so well connected. And a trajectory of the random walk there is doing a lot of damage. So it's hard to show that the U star, so for when U is small, the vacant set percolates. And this has been, so this was an open problem from a paper of mine. This has been solved in this paper where I quoted this H bar is strictly positive. Well, as a consequence of that, it's showing that on this thing, which is it's a borderline, it's a case where it's not very connected as a network, well, it works. And there is a whole, so you need some transients, you need some kind of volume assumptions and certain scalings to have the heat equation behave in the right way.
Mathematics seems, I'm not expert.
Yeah.
Mathematics seems clearly highly dependent on the underlying geometry of the graph.
Of course. This is this U star depends on the graph, and that was so even in the.
I guess some universal result, but the technique will be very different.
But you see, any no. It's like okay. Take percolation on ZD. It depends on the dimension highly, very much. So there, of course, if you change the graph, you have different things that happen. But there is a kind of whole degree of generality of results that persist. And there are class of graphs that behave in a good way and other class that behave in a different way. But this is normal. I mean, no one expects that random walks on all graphs behave in the same way. If you are a random walk on a tree and where there is a kind of exponential growth, it's a very different being from the random walk on Z3. So you have a velocity to go out to infinity. So there you can also, these random interlacements, you can define then on anything which is a transient graph.
So there is some high-level universality.
Yeah. So the object was constructed right away on a very general, but for the talk today, it would not have been constructive to go into that, that kind of abstraction. And I think the bean and the termite was carrying already a piece of the message, and after, thank you.
Are there any other questions? Yes, Philip.
I don't know if my question is
Yes.
very relevant. But
Yes.
isn't there a key difference between the dimension 2 and the higher
Yes.
dimension?
Yes.
To see connected?
You are very right. So it's a whole different kind of ball games. You see, like the result where there was this En to the d minus 2. In dimension 2, well, it's power law decays, and it's a very, well, the Gaussian free field, for instance, is exploding, so you only find it in boxes. So it's a different kind of universality, which is taking over. But there are some results on, for instance, concerning both random. Well, you can define some notions of random interlacements, and there has been several works, and some notions of Gaussian free fields and percolation. Okay, several authors, Jan Ding and Pierre-François Rodriguez, and the Comets and Popov, they have looked at it. But you are very right. It's another, so here it's the difference between transient and not transient. It makes a world of a difference. Yes.
Thank you.
Very.
Okay, so well, if there are no further questions, let me thank again. Let us thank again Professor Sznitman for this wonderful talk.
Thank you. Thank you. Okay. Thank you. Bye.